think you are muted.
Thank you. Can you hear me now?
Yes, sir.
Okay. Good. So let's take a look at the single carbon ligands, where a single carbon is attached to the metal. We spent quite a bit of time talking about how carbon monoxide is a unique ligand. And then, of course, we quickly moved on to alternatives to carbon monoxide, because carbon monoxide itself cannot be varied very efficiently and creatively. So we talked about how RNC is a good ligand, but in reaction media, it gets converted to species which are Fischer carbenes. Okay, so it gets converted to Fischer carbenes. And we also noted that there are some carbene ligands which were labeled as Schrock carbenes, and they were distinctly different from Fischer carbenes because they had no stabilizing ligand or stabilizing group on the carbon which is attached to the metal. And today we are going to talk about N-heterocyclic carbenes, most of which have got two nitrogen substituents on the carbene, which is coordinated to the metal. And in addition, there is a cyclic system which is stabilizing the N-heterocyclic carbene. So let's take a look again at our isocyanate. When we discussed the isocyanate, we said that there are several resonance forms, and one of the resonance forms was one where there is a carbon bearing the positive charge, and that explained why if you have a nucleophile, the nucleophile would attack the carbon which is having the partial positive charge, and that in turn will lead to an intermediate like this. When we had a carbon monoxide ligand, in fact, the oxygen and the NR-AR group, these two groups are actually equivalent. They are equivalent electronically, and so it's not surprising that you can have a nucleophilic attack by an aryl lithium or an alkyl lithium on the C+. That was in fact the basis for forming the Fischer carbene. On the other hand, the Schrock carbene had a slightly different structure. So let me just reinforce this fact. The carbon has got a positive charge, and in addition there is a lone pair bearing heteroatom sitting on the carbene carbon, either one or two. And this lone pair can pump in electron density into the carbene carbon, and that could be a stabilizing force. So essentially what you have is a carbon which is a carbene which is having an empty orbital on the carbon, and this empty orbital has got X groups which are capable of pumping in electron density, and there is a metal atom which is also capable of pumping in electron density. So the carbene structure in which there is an empty orbital on the carbon is sufficiently stabilized by electron density flows in three different directions. The Schrock carbene, on the other hand, is very, very different, what you are having is a carbon which is not having anything to stabilize that MTP orbital. If there is an MTP orbital there, it cannot be stabilized. You also notice that the Schrock carbene is having a early transition metal. In fact, most of the Schrock carbenes are made with early transition metals. They're more susceptible to air and moisture. They're more susceptible to air and moisture. They get readily decomposed. And in addition, they can be electron deficient. At the metal center. So these seem to be very strange complexes. Granted, they are very reactive, but nevertheless, they are, they have been sufficiently well characterized. So you cannot say that they are not present, not stable. They are stable enough to be characterized spectroscopically and using X-ray crystallography. In addition, if you look at the reactivity of the Schrock carbene, they are very reactive towards species like aldehydes and ketones. And what they're capable of is the transfer of this group, onto the aldehyde or the ketone. You are ending up with the oxygen on the metal. Oxygen is transferred to the metal. And so this is very much like the Wittig reaction. If you remember, the Wittig reaction had a CH2 or a CHR group on the phosphorus, and the oxygen was taken up by the phosphorus because the phosphorus was oxophilic. So you have very similar situation. The tantalum is now an early transition metal, and it's also oxophilic. So it's not surprising that the oxophilic metal picks up the oxygen, and the two carbon-containing species combine together to form an olefin. So what that implies is that there is a very different reactivity for the Schrock carbene, not surprisingly, compared to the Fischer carbene. The species that you form as an intermediate, this is really an intermediate because it quickly polymerizes. The tantalum double bond O is not as stable as a single bond O species. It quickly forms a polymeric species, which is indicated in this slide. And you should be able to understand why a tantalum 5 species is stable in this form. So let's take a look at and analyze this reaction a little closer. What we are saying is that if I can write it in this fashion, where the metal and the oxygen groups are juxtaposed, and the two carbon-containing species are juxtaposed, you find that there is a delta minus sitting on the Schrock carbene. If you remember, the Fischer carbene had a delta plus sitting on the carbon, and it was actually a nucleophile which was attacking the carbon. Whereas now, what we have is a delta minus on the carbene carbon, and that is attacking the ketonic delta plus charged C on the ketonic carbon. So this kind of the formation of a olefin with an M double bond O, I've shown you a single reaction, but there are a multitude of reactions that suggest that early transition metals having a Fischer carbene, sorry, a Schrock carbene will react with a aldehyde or a ketone and transfer a CH2 group or a CHR group very efficiently. And that is indicative of a negatively charged carbene carbon. At first sight, this sounds very paradoxical because you have an early transition metal, and that early transition metal now has got a negatively charged carbon. Okay, so where is this extra electron coming from? How do we account for this negative charge? One way to understand it is to look at the Fischer carbene as I drew it in the previous slide, as having 2 electrons in the sigma bond, which is formed with a metal, and an empty p orbital on the carbon. There's an empty p orbital on the carbon. And it is to this empty p orbital that you have electron density flow from the metal. On the other hand, we can think of the Schrock carbene as a slightly different type of a formalism. Let's take a look at this structure where you have only 1 electron here. You remember, a 1 electron attached to the metal will quickly pull the electron. Because the carbon is more electronegative, we made it a negatively charged species. Let's put the other electron on the carbene p orbital. So now I have 2 half-filled orbitals. And so what happens is, this is like having a C2 minus on the R group. And in both cases, the electron density has to flow from the carbon to the metal. So because the metal is electron deficient, it is really coordinating to a Cr2 2 minus. And that's the way in which we can account for this difference in the electro negativity and the electron density. Extra electron density on the carbon can be explained using this type of electron filling. Granted, this is only bookkeeping. We are merely moving electrons into different orbitals, but we are really talking about a different ligand altogether. So this is the ligand that we are talking about, Cr2 2 minus, and not Cr2 neutral species. So this is the difference between the Schrock carbene and the Fischer carbene. Is there any definitive way by which we can say that this formalism is right? One is the fact that computationally it has been shown that in fact this is a triplet carbene which is coordinating to the metal. That is the best way you can partition the 2 species. But if you look at some other electron deficient metals, there is a clear indication that C2 2 minus Cr2 2 minus is not an unrealistic formulation. Okay, so I have 2 papers which I will just show you briefly. One is uranium carbon. You can see that uranium is also going to be an early transition metal. Actually, it's a lanthanide, but actinide, and it is in the left side of the periodic table. So we can say that it is an early transition metal or an electron deficient center. So let's take a look at how it can be described. This can be really described as a situation where you have a C22 minus. I think I am missing one slide here. Let me see. Yeah. So in the F element complex, the ligand that was present was in fact substituted carbene, which had a P double bond S attached to the carbon. The P double bond S can stabilize this negative charge, this extra negative charge, even in the free form by movement of electron density in this particular fashion. So it's like having an adjacent ketone, okay? So you can stabilize that extra negative charge like that. And both bonds are in one direction. Basically, electron density is flowing from the carbon into the uranium bond. There are no filled orbitals on the uranium to push electron density back into the empty orbital on the carbon. So this is a case where you have, just like the halogen, it's not an unusual thing that we're talking about. Even in a halogen or an oxo bond with the transition metal, you have electron density flowing in the same direction in both cases. Okay, both in the sigma bond and in the pi bond, the oxygen is giving the electron density to the empty orbitals on the metal. So it's similar situation, but only thing is this time it is a carbon which is doing that. So these carbene complexes are very different from the Fischer carbene complexes that we have talked about earlier. Now, here is the structure of the uranium carbene compound that this is different from the P double bond S, but there is another compound where you have a Wittig type situation. This is a Wittig carbon. Let me write the ligand. PH, CH3, CH3, CH2 minus P plus. Okay, so it is best written like this. And what they have here also, in this case also, there is a partial double bond character between the carbon and the uranium. Okay, so let me go to a slide where I want to say that metal complexes with a carbon ligand should not be generalized as one type or the other, because the ligands can modify the reactivity of the carbon which is attached to the metal. So it's very difficult to generalize these things. What I told you is true in most situations, but take a look at this reaction, which we have already discussed once in a previous class. What I have done is I have removed a H minus, removed a hydride. Why? Because you have PPH3C plus, which is becoming CPH3H. Okay, CPH3 plus is becoming CPH3H. That means an H minus must have been removed. So if an H minus is removed from this, it is a positively charged species. And in fact, this is the isolated complex. So it is a positively charged complex. So everything is fitting the bill, except now think about it. This is a shock carbene. By shock carbene, we say that there are no heteroatom substituents on the carbon. But you have generated it by removing a hydride. So it cannot be a negatively charged species. So you have a contradiction here. But let me quickly add that rhenium is in fact a D7 species. So it is a slightly different situation. It's not a situation where you have an early transition metal. So you have, if you have a late or a middle transition metal, a CH2 group is in fact a Schrock carbene by definition. It is true, but it is not necessarily going to behave like a CH2 minus or a CH2 minus coordinated to the metal. So we have to be very careful in generalizing things. We have to look at the electron count on the metal before we decide whether it is going to behave like a CH2 minus or whether it is going to behave react with a nucleophile or an electrophile. So with that warning, let me just proceed to N-heterocyclic carbenes. N-heterocyclic carbenes, there is no doubt, there are two heteroatom substituents on the carbon. Okay. In fact, these carbenes were generated very early by heating this molecule and elimination of chloroform. Elimination of chloroform led to a carbene. Unfortunately, this carbene was not stable, although people thought that it would be stable because there is a pair of electrons on each nitrogen which can stabilize the empty orbital, but that was not stable, it quickly dimerized. And it was this compound which was isolated. And interestingly, if you remember, this molecule will break down in the presence of iron carbonyl to give you iron carbene complex. This, in fact, is an N-heterocyclic carbene. It's a cyclic compound, cyclic ligand. It's got two nitrogen donors which are stabilizing the carbene, which is attached to the iron atom. So this is great, but unfortunately, this is the only ligand which can be generated in this fashion. So it did not excite chemists or generate a lot of interest. It was the discovery made by Arduengo in 1991 that really made a big breakthrough in carbene preparation. What he did was to generate a stable carbene that could be isolated. As I told you earlier, if you have a ligand that can be isolated and kept in the lab, it makes a world of a difference. You can do a lot more chemistry with it. So this is the precursor, the imidazole cationic species that he used to generate the cation. What he did was he removed the proton using sodium hydride, NaH-. And that is one way in which you can remove the species H2 as a gas. So you have a carbene which is now stabilized by the presence of these huge adamantyl groups on both sides. So this carbene is in fact protected sterically from reactive species. And the reverse reaction is not possible because the hydrogen is left. So we have NaX precipitates and resulting in a carbene which is stabilized. Now let's take a look at the species a little closely. In fact, the imidazole cation that you have, in fact, is an aromatic species. You have a 6-pi electron system. Why? Because you have two lone pairs, one on each nitrogen, and you have a double bond. And you have a vacant orbital. Okay, you have a vacant orbital here. So if you look at the number of electrons in the cyclic system, you have 6-pi electrons. You have 6-pi electrons. It's a aromatic system. Now, the aromatic system is perpendicular to the plane of the ring system. The ring system is a 5-membered ring, which is in the plane of this screen. The pi system is perpendicular to the plane of the screen. Okay. And so it's completely independent of what happens in the sigma framework, where you have removed this hydrogen in the sigma framework. So this is a sigma orbital which will be in the plane on which the ring system is present. Perpendicular to the plane, there are 6-pi electrons. That's unaffected. so what it means is the 6pi electron system is unaffected and it remains intact in this ring system, and you have a pair of electrons which is sitting in the sigma orbital of the ring system, which is orthogonal to the pi system. What was quickly realized was that apart from adamantile, you could also have other species like I think you can have a mesotyl group. You can even have a simple phenyl group, and you can still isolate this 6pi electron system and isolate it and keep it. Dimethyl phenyl could also be prepared. So this is a big breakthrough because you now have a variety of ligands that you can generate, and what followed was a flurry of activity. And not only that, it was known that this ring system can be generated by a variety of ways. This is described in the book by Elias and Gupta. So I will tell you briefly if we have time, but you can look it up. So this ring system is easily generated, and it is easily deprotonated, and the carbene generated in situ. And to add to that, you can put it in a bottle if you have sufficient steric bulk protecting the carbon. So what is happening is that there is in fact a resonance stabilization of this ring system that you can easily visualize, very much like the Fischer carbene that we talked about. So the empty orbital is stabilized by the delocalization of the lone pairs, and you would still retain the 6pi electron nature of the ring system. So you have absolutely no problems. And there is, if you look at the lone pair which is sitting in the plane, that can be used as a donor orbital for any metal. Okay, so you have a very nice ring system, and it is tempting to attribute everything to the ring. So somebody did a calculation, and this is Angwati Chemi paper which appeared some time ago. I have forgotten to put the reference, but I'll do that. What they showed was that the heteroatom substituent was the major contributor to the stabilization. That stabilizes the system by about 87 kilocalories per mole. So if you look at the singlet CH2, which is, by the way, a CH2 would be a triplet CH2 in the ground state. So a singlet CH2 would be higher lying in energy. But if you make it doubly substituted with NR2 groups, it would become a singlet, and that would be the most stable form. And that is stabilized by 87 kilocalories per mole. If you tie this up in a ring system, that gives you only 6 kilocalories per mole extra energy, extra stabilization. But if I make it aromatic by adding a double bond, then it gives me 20 kilocalories per mole stabilization. So you see that this stabilization of this N-heterocyclic carbene is a combination of 3 factors. One is the fact that you have heteroatom substituent. The other is the fact that you have a double bond. The third factor is the formation of a ring system to make this aromatic ring, which will have some extra stability. So N-heterocyclic carbenes, like I said, are stable. They can be easily prepared. We looked at the first method of formation, which is simply removing the proton using a base. H- is also a way to remove it. Here you can also use triethylamine or bis-trimethylsilyl amide. You can use a variety of species to remove this proton. In fact, it is easily removed because removal of that does not affect the aromaticity of the ring system. In addition, it was also possible to have this chloro compound made, and the chloro compound could also be dechlorinated using mercury. Now, people are moving away from mercury, so this would be a less preferred method, but just to put it on the record that early methods of synthesis involved all kinds of reactions, primarily the base promoted deprotonation, but you could also have extrusion reactions. This is very similar to the HCl CCl3 fluoroform extrusion. Only thing is you now have an aromatic ring being extruded, C6F5H. So that's just pentafluorobenzene. That's a better way to say it, pentafluorobenzene. So that's extruded. You can also extrude carbon dioxide from this species. So there is a large number of ways by which you could generate this molecule. The last and the final one is a rather drastic method. You can reduce the C double bond S, you can remove it as potassium sulfide, and you can generate a carbene. This would be a very drastic way of generating it, but nevertheless, it's possible. So you can see that a whole bunch of ways to make the heterocyclic carbene result in the popularity of this ligand. And right now, it is one of the most popular ligands in the literature. You find it just about in every other metal system. But recollect that there are some unique steric and electronic properties for this ligand, which is very different from other ligands. So that's another reason why it is popular. It gives a different flavor to the metal complex. We'll see exactly how. Just look at this system. This is a mesetyl bis mesetyl imidazolium salt, 1,3 bis mesetyl imidazolium salt. And this imidazolium salt has got a proton which is sitting here. And as I told you, this proton is in the plane of the ring system. We don't have a time to look at the 3D structure, but you can look at the 3D structure. You will find that the proton is buried deeply and it's well protected by these two methyl groups which are sitting, the two methyl groups which are sitting here. If you deprotonate it, this deprotonated species is also sterically protected by this methyl groups which are sitting here. In fact, if you look at the space filling model, you find that the space filling model, the carbene carbon is kind of buried inside. You can hardly see it. I have generated this using mercury. I will send you the zip file for this. You can visualize it yourself in the 3D form now that you've all learned how to manipulate 3D structures using a zip file. So this molecule turns out to be, this ligand turns out to be a very stable species, and is a surprising thing is it complexes to a metal, and if such a bulky ligand is complex to the metal, you would hardly have any space around it, right? And that, to me, that is more surprising. Of course, because you can generate it in situ, you can have less bulky groups. Here in this example, I just have a dimethyl group in the imidazolium form, and I generate it in the presence of palladium acetate. And you do not even have a very strong base. You just heat it with palladium acetate and the sodium, and in the presence of sodium iodide. Sodium iodide is added because you can have I- as a good bridging ligand that generates this palladium iodo complex, which is what is isolated. as a bis NHC complex. Okay, so this is a very nice complex that is isolated. And now I want to introduce another principle here. Whenever you have a dimer like this, where you have a halo bridge or even an oxo bridge or a acetate bridge, if you want to break it up, the best thing to do is to add triphenyl phosphine. In organometallic chemistry, this is a standard practice. You add another good ligand and it breaks the bridges and you form now a mononuclear complex. The reason why this happens in such an efficient manner is because PPH3 is a very good ligand as far as crystallization goes. PPH3 has a property of interdigitizing, which means the three phenyl groups, in fact, will interlock with each other. So it's like a gear system, okay? So these two can pack very efficiently in a three-dimensional structure, resulting in very good crystal structures. And these crystal structures can be precipitated, I mean, because they form nice crystals, they precipitate out of the reaction mixture, and you have driving of this equilibrium in this one direction. Okay, so this equilibrium is pushed in one direction, and you have very good yields of this monomeric complex now. So for the stoichiometry, you would get 2 of this if you add 2 of PPH3, and that's what you end up isolating. So like I said, this is a general way to break up dimers. You will come across this again and again. Many times it's convenient to have a halo bridge species isolated to start with, and then you add, after this becomes a way of purifying the whole metal complex. Okay. So sometimes it's convenient to make an intermediate complex. People make silver N-heterocyclic carbenes with Ag plus or with mercury, and then transmetallate it to a metal, transmetallation. This turns out to be a convenient way of making the complex, because direct transfer to a transition metal sometimes is not as efficient as transfer through a silver or a mercury salt. I really do not have a good explanation why this has to be done in this fashion, because thermodynamically we are going in the right direction. But still, in spite of that, transmetallation seems to be an efficient method for making mini carbene complexes. Here in the second reaction that I've told you, it's elimination of hydrogen that happens. That, of course, will lead to a one-way reaction, because hydrogen escapes from the reaction medium. So let's proceed. I will briefly tell you what happens to the geometry. I already told you that because you have 2 bulky groups around the carbene carbon, this becomes a protected carbene, and that's one reason for the stability. Another thing that we should bear in mind is that for a singlet carbene and a triplet carbene, the CCC angle, or the NCN angle in this case, has to be different. Because if you have an MTP orbital, then you have an sp2 hybridization. If I have a triplet carbene, then I have an sp3 type of hybridization. So for an sp3 hybridization, the angle is 109 degrees. For an sp2, it is 120 degrees. For a 5-membered ring, 109 degrees would be actually better. So there is some amount of strain in at the carbene carbon. And when you coordinate it to a metal, part of this is the enforcement of a 120 degree, or rather an sp2 hybridization, results in small amount of geometrical changes. Okay, so bond distances and bond angles change slightly, but keep this in mind that if you want a 120 degrees for a carbene carbon, this is in fact as introducing some amount of strain in the system, because you have a 5-membered ring, it's much smaller. Okay, so let's proceed. Keep these things in mind, and then let's take a look at the character of this ligand. If I put it in CrCO5, for example, I can measure the carbon monoxide stretching frequency trans to this carbene. So I have NHC here, and I have CO here. I'm measuring the new CO of this, and that's 1972 centimeter minus 1. If I have a carbon monoxide trans to another carbon monoxide, I have 2108. What that tells me is carbene is not a good pi acceptor, or this is a very good sigma donor, which is enriching this metal with a lot of electron density, and so the metal is pushing electron density into the carbon monoxide. You should remember that there is a sigma and a pi component. This NHC has got a sigma donor ability, but the electron density is being pushed into the pi system of carbon monoxide. But nevertheless, the electron density on the metal is being pushed, and so it's possible that carbon monoxide is having greater pi star electron density here, and that's why you have this lowering of the CO stretching frequency trans to the NHC. So this CO stretching frequency goes down specifically. We should compare it with what happens when you have a Fischer carbon. So here you even have a greater amount, and this greater degree of pi star occupancy in the case of the Fischer carbene is clear indication that this is in fact a poor pi acceptor. Because here you do not have that amount of electron density being pushed into the sigma framework also. In the case of the NHC, the carbene seems to be very electron rich. I will come to the measurement part in a few minutes, but this is a combination of two factors. That's all we need to remember at this point. I will talk about some more measurement factors, because right now we are only talking about the pi star occupancy. Okay, let's take a look at some of the other factors. To quantify electronic effects, Tolman, the same person who measured the Tolman cone angle, figured out that cone angle is only a steric parameter. So you want something to measure the electronic effect of the ligand. So in order to measure the electronic effect of this ligand, let's take a look at the CO stretching frequency in nickel tricarbonyl complexes coordinated to the ligand. Nickel tetracarbonyl has got a stretching frequency of 2060 centimeter minus 1. Okay, so this is 2060 centimeter minus 1. If I put a ligand and the stretching frequency goes down, that means this ligand is not a good pi acceptor. Okay, so this CO stretching frequency, there are in fact two stretching frequencies. One is a symmetric stretch, the other is an antisymmetric stretch. Usually the symmetric stretch or the higher frequency stretch is taken as the one which is the TEP value. So people have measured the TEP. This is just given not as delta, but it is given as a value in centimeter minus 1. And you find that the stretching frequency sometimes even goes up, which means that your ligand is capable of competing with the pi accepting character, is capable of competing with the carbon monoxide also. So I told you that carbon monoxide itself has got 2060. So some of these are good pi acceptors, apparently. Okay, with dimethyl, it seems to be as good a pi acceptor as carbon monoxide. Here is a list, a bigger list of carbon monoxide stretching frequencies for a variety of N-heterocyclic carbenes. The N-heterocyclic carbenes are usually imidazole type. So I stands for imidazole. Okay, so you have N, and this R group is the one that is specified. Okay, when it says IME, R equals ME. If R equals let me take another example, mesitide. It will be IMES. Okay, so let me see, let me identify IMES here. When they put S IMES, it means there is no double bond. That means it's a saturated system. Mesitide, mesitide. This is S IMES. So I don't have IMES here in this, but a whole bunch of a variety of carbene ligands are listed here for you. And what this tells you is that carbon monoxide stretching frequency in NiCO3 is convenient because NiCO4 can be just treated with that ligand and it immediately forms NiCO3L. And IR stretching frequency is measured up to 0.1 centimeter minus 1 accuracy. So very often you find stretching frequencies listed up to the second decimal place. So but I have uniformly, here is IMES. Okay. The reason why IMES is different from imethyl, for example, is because it's very simply because of the fact that you have a very strong steric component which will prevent the ligand from coming close to the metal. Okay, so this distance is longer, so the bonding is probably, the pi effects cannot be very strong, and so the CO on the trans side is having a lower stretching frequency because of better pi accepting character. So in general, it has been found that N-heterocyclic carbenes, you have electron-rich neutral sigma donors. That's the characteristic of N-heterocyclic carbenes. And you have poor pi acceptors, poor pi accepting character. I told you something about the ring system. If I vary the ring system, I can vary the angle. If I make it slightly larger, as in the case of the cyclohexyl substituted ring system, diaza hepta ring system. Here I have the ring system is not having any unsaturation. Here I am having unsaturation. Okay, and you find that the frequency of the carbon monoxide is going down, and so this is indicative of the fact that you have less pi electron density being pushed into the nickel, and so these are poorer and poorer pi acceptors. That is consistent with the fact that you can push more electron density in this larger ring system compared to the shorter ring system here. If I take this ring system, this angle has to be 120 degrees to be stable, but you have a much smaller angle. So this is a strain. There is a strain in this system. Whereas here, because the angle is much larger angle, you can have more stabilization from the both nitrogens. Stabilization from nitrogen donation. And so the carbene carbon is not as good a pi acceptor compared to the carbene carbon here. So as you increase the pi accepting character of this carbene carbon from the nitrogen, you reduce the pi donation into the carbon monoxide, and CO gets more electron density in the trans position, and as a result you have a lower stretching frequency. Most of the time it is the A band, which is not most of the time, all the time, it is the A band which is used for this measurement. Now, before I end today, I should tell you that not all nickel tetracarbonyl complexes, at the time that this was developed, other people also developed other methods of measuring stretching frequencies. One of them was an iridium complex, and the other was a rhodium complex. And usually all these measurement factors have parallel stretching frequencies, parallel reduction of stretching frequencies, or parallel increase of stretching frequencies. And they all suggest that the carbon monoxide trans to the NHC is the one which is more significantly affected by the sigma donation and the poorer pi acceptance from the NHC. Okay, so one can even tune the electron density donation by using such redox active substituents like ferrocene. Somebody has also done that. That changes, if you oxidize the Fc to Fc plus, then the frequency changes by 11 centimeter minus 1. That's a significant amount. Okay. If you make it cyclohexyl compared to phenyl, then again there is a 11 centimeter minus 1 frequency difference. So you make it electron rich, then you have greater electron density flow into the metal. So you have more electron density flow into the metal, then you have greater pi star occupation on the carbon monoxide, and so the stretching frequency goes down. So you can modulate these electron density on the metal, and this is reflected in the carbon-13 chemical shift also. This is another way by which you can measure. So people have used all kinds of measures to figure out how much electron density is going into the metal. And I should give you a reference. I'll give you this. This is a reference which is there. There is also another paper by Frank Glorious on the measure of all rings. I think I have it in the next slide. But these are papers which are going into great detail about how much electron density is pushed into the metal from an NHC ligand system. Okay. Finally, the steric features are slightly different from a phosphine. In a phosphine, the metal is on one side, the R groups are on the opposite side. Whereas note here, the metal is on the same side as the R group. So this is towards the R group. So the steric influence of NHC is even greater. And it was Steve Nolan who figured out what is called the buried volume. So instead of using an angle, he used a volume, and it is more popular for NHCs. And the reason is very clear. The R groups are pointed towards the metal and they influence it significantly. These are measured using X-ray structures, as opposed to ball and stick models. So finally, let me stop here and find out if you have any questions. We have basically covered a lot of ground, but at the current state, NHCs are superheroes. They are used by everybody in order to tune the electronic and steric property, as I mentioned here. The ligands are easily made. They are very good in terms of sigma donation, and you can generate it in situ and make a variety of catalysts. So I'll stop here. Any questions?
Sir, can you again explain the donation with the ring size, the relation between the electron donation and of the carbon NHCs?
So this slide, what I mentioned was the angle in a 5-membered ring system is smaller. Okay, it's close to 109 degrees if you want to have a planar ring system, right? So there is a certain amount of strain, and to make a double bond around this nitrogen and carbon is a strain, right? So it's not as easy as you can do it with the larger ring system where the angle has been widened now. The larger angle makes it more, or rather less, strained to have a double bond, N double bond C. And on both sides, the nitrogen can push electron density into angle which is closer to 120 degrees. Okay, and there is a partial double bond between the two nitrogens and the carbon. This satisfies the empty orbital which is present here on the carbon, and it is not as good a pi acceptor, not a good pi acceptor, when you have a larger ring system. Why? Because you can have satisfaction of filling the electron density into this MTP orbital from just the nitrogen. You don't have to get it from the metal atom. And if you don't have to get it from the metal atom can give it to the carbon monoxide. If it goes to the carbon monoxide, stretching frequency goes down. So the larger ring system, the stretching frequency goes down, and the smaller ring system, the stretching frequency is higher. So just within this group, if you compare the larger ring system, the closer the angle is towards 120 degrees, the lower the stretching frequency.
Okay.
Any other question? I want you to look at the answer papers and your answer papers and the key that I have given. Arpita will start grading them from today. So if you don't hear any questions about that, we will start grading it and giving you back. You can also grade it yourself. This is now it's made possible because you have a copy. We also have a copy of what you have given. So, okay.
Sir?
Yes.
I have one question regarding the evaluation pattern.
Yes.
In the first question, in order to explain the acoustic interaction, in the evaluation pattern, it was mentioned that we need to talk in terms of metal hydrogen distance. But but will it be wrong to explain the acoustic interaction in terms of the carbon hydrogen distance or elongation, carbon hydrogen elongation at the beta position when compared to the uncoordinated carbon hydrogen bonds?
There is nothing wrong with it. There's nothing wrong with it, except that this is usually a little more reliable. I don't see anything wrong with it. Okay, whatever argument you used, if it's consistent with the, if you compare it with the uncoordinated CH bond, it is a valid point.
Okay, okay. Okay, sir, yeah. Thank you.
Sir, I have a doubt.
Sri Vignesh, you're not very audible.
Just a second. Can you hear me now, sir?
Yes.
So I have a doubt about the pi-accepting nature of comparison between a Fischer carbene and N-heterocyclic carbene. So in one of the slides where there was like an oxygen-based Fischer carbene, we saw that was a poorer pi-acceptor than the N-heterocyclic carbene. Why is that so, sir? Like here we have two heteroatoms which are nitrogen, which is a better donor. So shouldn't this be better at like poorer pi-acceptor?
Yeah, very good point. Very good point. So probably it is the ring system which is causing this difficulty, because here when you have no ring system, so let's work this backwards. Where's my pen? Yeah. So here you have more electron density going into the, so let's put it like this, less here and more electron density is flowing here, right? So if more electron density is flowing here, that means this double bond character is better, right? It is not competing with the trans carbon monoxide, right? In a ring system, like I told you, that is strained compared to this one in the non-ring system. So that there are so many factors. It is the nitrogen you're right, compared to oxygen, which is more electronegative, this donation should be poorer, but then because it's an open ring system, it's an open acyclic system, the angle can be exactly 120 degrees. No restraints. Here it cannot be 120 degrees. You cannot have the double bond character.
Yes, sir.
Maybe that is one reason. Okay.
So if we are like, the main advantage of using N-heterocyclic carbenes is the ease of preparation of the ligand, and that's the main reason why it's very popular, right? That
is one reason. The steric protection, the electron density variation. See, when we have still not started talking about catalysis, but the moment you want to have tuning of a catalytic property, you want to change the ligand steric and electronic effect in such a way that you get better catalysis.
Yes, sir.
That is the advantage of N-heterocyclic carbon. And you can have so many variations.
Yes, sir.
Okay. Any other question? Otherwise, we'll close. We'll continue on Wednesday.
Sir, the difference between this Fischer and the NHC, can it be explained by the cross conjugation? Like the cross conjugation is not as much effective as the normal one if there is one donating group. Like, can it be explained in that way also?
I don't know what you mean by cross conjugation.
Like if there are two like electron donating groups, then the conjugation is not as effective as one Like it does not increase the stability that much.
No, I don't think that's a very valid argument. I would say that if there are two groups, then the stability should be better than having one group.
Sir, I think the way he's talking, like that to cross conjugation argument would be useful for looking at N, what happens to the N atoms, but it wouldn't be very useful for measure for carbon. Like carbon, regardless of whether it has cross conjugation or not, that would have.
No, we are looking at the empty orbital on the carbon. How good acceptor orbital it is with respect to the chromium. Okay, that's what we are looking at, and that definitely is not favorable for explaining this stretching frequency that I have in this particular slide. Granted, I am doing all the arguments post experiment. If you ask me to predict it ab initio, I would have a tough time. Okay, so given the experimental data, how do you understand it? That's what I'm looking at. Okay, thank you very much. We'll see you all on Wednesday.